a static code analysis startup called CodeBeat. We do hosted automated code review based on static analysis. But this is not a product talk. What I'll try to do during this talk is first introduce you to the concept of static analysis, why it's important, and how we can do it. And then I'm going to show you how we try to do it between languages. So what we do as a product is fascinating, but it's mostly irrelevant to what I'm going to talk about. So before I go to the gory details, let me ask you a kind of charged question. Who we are. Are we programmers? Are we IT people? Are we coders? Are we hackers? Are we ninjas? Like if you get, LinkedIn contact requests from recruiters, sometimes you feel like you're like, a paid assassin because they talk about you as if you're a ninja, or that you do drugs, sex, and rock and roll because you're a rock star. So are we rock stars, or maybe you're software engineers? And despite we like to think of ourselves as engineers, software engineering is an aspirational term from back in the 60s. And it came from people who thought that one day we could build software the way we could build bridges. And there's a wonderful piece on the internet called Programming Sucks. And there's a satire about a team of people who try to build the bridge the way they would build software. So the other way around, and you can imagine how it ends. It's a suspension bridge that has no suspension, so they built a pylon somewhere just to hold the whole thing. But, they kept the suspension because you never know. So that hasn't really worked, has it? But the thing about real engineering is that atoms are much better at communicating constraints than bits are. If you're working on a bridge, it's either going to collapse or it's going to last. But it's not somewhere in between. It's not a Schrodinger's cat. Most code bases, though, they are like Schrodinger's cats. They are in a limbo. They are somewhere between totally collapsing and working just fine. It's not like most code bases, unless you're Sony, they don't go with a bang. They go with a whimper. And yet, despite the sorry state that we are as engineers, we are more and more influential over what's going on around us. Namely, software is connecting us with each other. It helps us access information, and it is built into medical devices that save our lives, and software kills our enemies as well. That said, as a society, we find it appropriate to jail a doctor who makes a medical error. So far, I haven't heard of a software engineer jailed for introducing a bug, although maybe in North Korea they do that. It's hard to say. But I wouldn't be surprised if one day that's actually what's going to happen. If your rocket hits some different target that it should have hit, maybe you'd be jailed. I had a previous boss of mine was a defense contractor one day, and he says, every time I see the footage of a rocket hitting a target, it's one of mine probably, and I thank God that this is hitting the right target and not some of our guys. Maybe if it hit his guys, he'd be in trouble, I don't know. We still don't know how to treat those programming errors as a society. So we're this growing army of people who write software, but if we are an army, we look pretty much like this. And I'm not trying to be an elitist because I'm this guy here. We come from different walks of life. Most brilliant people that I worked with had no CS degree. I do have a CS degree, but I didn't pay attention. But they bring really interesting perspectives. Musicians, PhDs from the fields of physics and all that. They bring interesting perspectives, but we as a profession lack the rigor that proper engineering kind of assumes. When I studied my CS degree, the Engineering Association of Ireland denied the school status of engineering because they said software is not engineering, right? And you don't use tools. We have tools as engineers. It turns out, though, that over the years, since we had this aspiration of being an engineering community, we built ourselves a ton of tools. And those tools are both software tools and mental tools. So you can think of tools like IDEs, which are software tools, and they do an amazing job. If you've worked with IntelliJ IDEA, I mean, it's fantastic. Sometimes I just click on those bubbles just to see what it can do for me, and like I'm impressed every single time. But there's also mental tools like development methodologies, waterfall, extreme programming, agile, Scrum, what have you, Kanban. That's a mental tool. Design patterns, another mental tool to basically give standard solution to standard problems, because 99% of the time we work with standard problems. And if we work with a problem that is not a standard problem, we can think of a way of bringing it of turning it into a standard problem. So as in CodeBeat, we saw an opportunity in the fact that a lot of the tools that were used for static code analysis or code quality analysis were either difficult to understand, difficult to set up, or maybe they were not designed to work as a team. Maybe they just run on your local machine, but you couldn't share your result with your team. So the most value is lost because software engineering, to use the aspirational term, is a team sport after all. So we created a product called CodeBeat. And the way we approached it first is the way everyone approached it, which is taking all of the individual tools out there. There's a lot of good, great open source tools out there. You can try to bundle them, and you can do it in a hosted way on your server, and you can show the result and pack it into a nice UI, and lo and behold, you got, all those products that are out there. And they're good. Like for years we've been using that I've been using that in different companies, and they're decent. But the obvious limitation to this approach is that you're 100% reliant on someone else's work. And even if that work is brilliant, which sometimes it is, sometimes it isn't, different linters or different code analysis tools for different languages would report different things. So, you'd have this idea that metrics are totally different, like that totally different things matter in Python than in Ruby, which is obviously not the case. Those languages are like 99.9% the same. It's like us and chimpanzees. It's, there's hardly any difference between two languages, even though you might kill me after the session. So we decided to write our own things, and originally we wrote them for Ruby and Go, and it's a lot of work. It's a lot of work because analyzing source code is not as trivial as it seems. A lot of linters take a short path. Basically, they do some sort of regular expression matching or pattern matching per line or so. But it's a very limited approach. It's very unreliable. If you ever try to match HTML with regular expressions, you probably know what I mean. So the real approach is to start with lexing and parsing. And if you approach this is cuneiform from, I think, Babylon, but if you're an archaeologist and you can call my bullshit, that's even better. If you see something like this, and you know that it is a language, you can start by parsing this by splitting this language into individual tokens. And that's the first thing you need to know about the language. The first thing you need to know about the language is how to parse or how to split that language into the smallest possible parts, which are called tokens. And the the software that does it, the piece of software that does it is called a lexer. And in this case, lexer would probably look at the white spaces, right? And the white spaces would be somewhere here. But it will also know whether this is one token or maybe it's two tokens. So it would report it as, you know, correctly. So it's the first thing you need to know about the language. A lexer would take in the source file and it would break it into, you know, a stream of individual tokens, which is the good first step, but it's mostly useless for us because we don't know what those tokens represent. So the second step is parsing. And parsing is basically feeding that stream of tokens and trying to make sense of what it represents. Essentially, the tokens are then matched against what's called a grammar of a language. A grammar is a formal set of rules that govern what's legal in a language and what certain tokens would mean, and in common in different order what they would mean. So what the parser usually starts with is a formal definition of grammar. There are formal ways of describing grammars. BNF, Bacchus-Naur form, is one of them. Extended Bacchus-Naur form is a more advanced version. And based on this grammar, you can write a parser that essentially creates a tree. So parsing is a science on its own. You got all sorts of parsers, LL parsers, LLAR parsers, and that's a crazy science that I don't really understand because I didn't pay attention during my CS course. But anyway, parsing is a search problem, and it's trying to find a shortest, probably the only path between a stream of tokens and a tree. So if a stream of tokens, or if a source file looks like this, and lexer takes care of it, the parser will try to find the way between this and a legal parse tree, or abstract syntax trees. By the way, what language is that? Any shots? Swift, yeah, it is Swift. Well done. So it is a search problem after all, but there are multiple ways of approaching it. But hey, it's computer science. We've got a tree, and it, like, back when I look at my CS degree, it feels like 90% of my time was spent working with trees. It's like if I started just, you know, if I was supposed to be a lumberjack, pretty much. It's black trees, red and black trees, balanced trees, binary trees, and, you know, Fibonacci trees, and all sorts of trees, pine trees and poplar trees. But anyway, if we got a tree as software engineers, we know what to do with them because we're really good with trees, right? We're lumberjacks. But when you look at this tree, there's one thing that could strike you, and what could strike you is that in this parse tree, too bad you can't see it, I can't see it either, but I'll highlight it in a second. In this tree, you can see that certain tokens or certain nodes are different than others. And lo and behold, the ones that I marked in green come directly from the source file that I fed into the parser. And these are called, sometimes they're called terminals, sometimes they're called lexer tokens. They always come as leaves. They are always coming at the end of each branch. But what could strike you as well is how few of them there are. The bulk of the tree is red, so the red stuff represents stuff coming from the parser. So you can think of the green stuff as being the content of the tree, and the red stuff being structure or meaning of the tree. So once you've got this AST, abstract syntax tree, in fact, it's a parse tree because it has parts of things that play no role in the language, like brackets and stuff. So AST is probably not the right word for that, but still, it's how people call it. Once you have it, and it's a search problem, static analysis is a fancy graph traversal problem. All static analysis will work on these trees, and traversing them back and forth in fancy ways will yield really interesting results, and pretty much calculate all the stuff for you. And changing the AST will give you all sorts of refactoring opportunities. You can pretty much refactor the code just by moving things and seeing if they're legal. And if they are, well, that's the legal solution. And that's what tools like IntelliJ do for you. So what we did is we wrote fancy graph traversals or tree traversal algorithms for Go, and we were happy. We did that for Ruby, and we were happy. And here we are with 2 languages. We put a lot of effort into that. And now we want to support Swift and Objective-C, and shit, we need to do it twice more just to, support 2 languages. And then it struck us. We had a sudden moment of clarity. I'm sure you know this meme. But before I talk about the sudden moment of clarity we had, let's talk about aliens. So when aliens first landed in Roswell, or they crashed in Roswell in 1948, some people figured out it would be beneficial to be able to talk to aliens. And obviously, I don't know what happened in Roswell. I don't really believe in aliens that much, but there was a lot of interest in communicating with extraterrestrials. So a lot of intellectual effort went into the field of how do we actually talk to beings that we have no common ground with? So, aliens probably don't speak English. After a while, people figured out they probably wouldn't speak Russian either. And even more importantly, we have no shared experience. We probably have more shared experience with dolphins than we have with aliens because we live on the same planet. So what do we do to communicate with them? Namely, what do we do for them to see us as intelligent beings? How can we present ourselves as intelligent, and how can we start a conversation so that they assume that we're intelligent and we have a two-way, meaningful connection? And it turns out that we can make a few assumptions about aliens. When we send them a radio signal, we can make an assumption that they can, somehow receive that radio signal. Because if they can't receive it, we don't want to talk to them. Because they're not intelligent or not intelligent enough. So they're a technical civilization. If you're sending a stream of, a burst of radio, we're talking to technical people. And if so, we can assume that, they have devices that they built to receive that. And the way they must have built the tools is that they understood the reality around them. And the most basic understanding of the reality around you is based on what? Mathematics. So we assume that aliens speak mathematics, and we'll start with sending them bursts of digital or binary digits. Maybe we'll start with prime digits so that they'll see a pattern and they'll start thinking, it's probably coming from an intelligent source. But the assumption is this: we assume that we have a shared or a common ground with aliens because we must have accomplished the same thing. And how we accomplished that was mathematics, but we must have accomplished the same thing. So we have this common language that we can assume that there is a common language between us. And programming languages are exactly like this. That was our sudden moment of clarity. Programming languages are all the same. And they're not the same because of some transcendental or, monk in Himalayas just having a, some sort of meta thought. It is because they accomplish the same things. In every single programming language, you'll get things like if or some conditions, ifs, loops. We'll get code in procedures, split into procedures. There would be exceptions. There are languages without procedures, but we figured out it's a good thing to basically, separate chunks of our code into procedures. We would have namespaces, so we'd have classes and that sort of nice stuff. And this is something that is present in every single language. When we look back at our girl class, what it does is essentially it has a property. It's a name. It's a string with a question mark, means that it is a string, but it could also be null. It has a constructor which assigns a name being passed to the constructor to a property name of the class, of the instance. And there is a function, say hello, and if we give the girl a name, she'll introduce herself, otherwise she'll go all Arya Stark on us and says, a girl has no name. Okie dokes. So when we look at this and break it into an AST, we can see that certain nodes in that tree have certain meanings. And that meaning is a meaning that is kind of universal. A lot of the things here are not universal. They're very specific to the language. But there are nodes that are universal. And you can't see it here, but it says class declaration. A class declaration is obviously a namespace. And then there's a variable declaration inside the class declaration, and it obviously represents some sort of state. It's a variable, it's not a constant, so it can be changed. It is state. Then we do have a constructor, a way to basically create a new instance of a class. It's probably something that you have in every object-oriented language. You do have a function, so some sort of, discrete procedure, and you do have a condition. In this code, we do not have a loop, but we have at least 5 different meaningful nodes that we can, universally describe. Right. So let's look at an implementation of the same code in a different language. Again, what language is that? Catalan, yeah, it's Catalan. How do you know? Yeah. One of the things you can see is an implicit constructor, right? That's quite characteristic of Catalan. Again, it's a class. Catalan has implicit constructors, so you can, things that you pass to a constructor, to a primary constructor, will automatically become variables in this class, or if you pass a variable, you can also pass a constant. And there's a function that pretty much does the same thing. It checks if a name is null. If it is not null, the girl will introduce herself, otherwise she will go all Arya Stark on us. And when you look at the AST that is constructed from it, it is quite different. But it also isn't, because it has all the same meaningful nodes. You can see that there's a meaningful node for a namespace. It's also called class declaration, I suppose. Let me see. It is. And then the constructor is called constructor. No, sorry, primary constructor. State is a function parameter to the primary constructor. And then there's a function declaration. There's an if expression, which is a condition. And lo and behold, the code is roughly the same, and we have the same meaningful nodes, even though the tree does look quite a bit different. Right. So the whole concept was that if we take parse trees from different languages, all we need to do to feed them into one algorithm that'll essentially munch them as one, is to be able to annotate certain nodes. So bringing them to a common form, we use protocol buffers. Bringing them to a common form will allow us to consume them with one analyzer. What is done to us is it has allowed us to add support for 4 further languages very, very quickly. We started supporting Java, we started support Objective-C, Python was next on the list. So it went very, very quickly. And also, like, adding extra annotations basically allows us to quickly add support for new rules that we monitor for all languages. So we have, the same rule set for all languages, which is a value on its own, I think. So it is, all unicorns and rainbows. We got asked at some stage, can you get Catalan support? We got it on Intercom, and I was like, do we have a good parser? Yes. Okay, give us 2 weeks and we'll get you there. Yesterday we saw an inspiring talk about Elm, and I just put it on our Trello board, ideas, Elm support. Is there a good parser? I can write my own parser. How I can write my own parser is that if there is no parser that suits our needs, we can always use a parser generator like Antler. Antler is a fantastic API to work with. Every node is visited with 4 different rules. Enter every rule, enter that specific rule, exit this rule, and exit every rule. And for Lexer tokens, it has visit terminal. It's a fantastic API. If you know stacks, you can do everything, right? It's like sax parsing. If you've done XML sax parsing, if you're old enough to have done that, this is roughly what it is, and it's fantastic. We slapped that API onto our different parsers as well because it was so lovely. But there are some problems with some languages. And we assume that functions are unique, but sometimes they aren't. You have something called multibody functions. Any idea what this language is? Yeah, Elixir. More people know Elixir than Catalan. Good. We're adding Elixir support shortly. So it's interesting. It's a function with the same signature, but there are 2 of them. What's going on? And we haven't seen that before. We assume that functions are unique. So we had to come up with a new thing that, they're function versions. So we bundle them together and slap a condition node on every one of them that is not the first one, because it's like an if statement. It isn't, but it also is. Like, functional programmers will kill me for saying that it's a condition, but it is. Pattern matching is a form of condition. Another language that was not unicorns and rainbows was JavaScript. And it's because, not because it's a bad language, it's a good language, but it's badly misunderstood, because it's a prototype inheritance language that most people try to write in an objective way. And the problem with that is, and ES6, by the way, made things worse because it kind of reified things that, something like a bad understanding of a language or misunderstanding of a language. And the problem with JavaScript is that, one person's Ruby code looks like another person's Ruby code, but one person's JavaScript code looks nothing like another person's JavaScript code. So when we're trying to interpret some of the nodes in JavaScript AST, we're often confused, and we need a lot of context to understand what this guy was trying to do. Is that a function? Is that a namespace? Is that, what exactly is that? So sometimes we have problems with JavaScript, but we'll eventually add JavaScript support. And there's also PHP. And I'm not going to take cheap shots on PHP because, like, that's like flogging a dead horse. I actually did take a cheap shot now. Sorry. But what is the problem with PHP in terms of static analysis is that it's not really a language. It's what's called an island grammar. It's like, PHP is like, it can look like Java, like a proper language, interfaces and all, but it can look like total spaghetti, like it's not being a programming language, it's being a templating language, or it's like ERB in Ruby, or JNJ in Python, or Mustache in JavaScript, that sort of stuff. And it's kind of hard to figure out whether you're trying to use PHP as a templating language, or you're trying to use it as a programming language. It's not that obvious what you're trying to do. So we still haven't found a good way to, mold PHP into our framework. One way of doing that is basically, okay, if we figure out that what you're trying to do is templating here, we just ignore. And we only focus on programming parts. So that was it. I hope I could convince you that static analysis is a worthy pursuit. I hope I could try to convince you that you can do it in a language-agnostic way, because certain nodes have universal meanings. And maybe I just gave you this feeling that all languages are the same. That was not my intention. But that kind of is true. Thank you.
Hey, thank you for your talk. Do you know if there was any prior attempt at cross-language AST standard or something? And if not, do you have any plans on trying to release maybe some kind of specification of cross-language AST?
So there is an open source plugin system for Sonar. Sonar is also a static analysis platform, and it works for different languages. You can get open source version, and you can pay like hundreds, maybe not hundreds, but tens of thousands of euro for a commercial version. They do have some sort of language agnostic way of representing things, but it's more on a Lexer level. They don't do all that much parsing. Like when I saw, maybe they do something in their commercial stuff. I don't know, because I have no access to it. But when I saw what they do for open source, it was not that smart. In terms of open sourcing it, there is an ongoing discussion between ourselves whether we do it or not. But after looking at this presentation, I think you have a good idea of how you could do it, I suppose. We might do it at some stage and allow people to give us support for their language. Like if you write your own language and you want that supported by CodeBeat, maybe at some stage we'll just give you a format. You export your stuff into that format, and lo and behold, you have support.
Thank you very much. Give Marcin a round of applause.